All right, let's get right into it. Matrices. You see them, and they just look like a big old grid of numbers, right? But really, they're these incredibly powerful objects that secretly describe how space itself can be starched, squished, and rotated. And like any good secret, they have a code. Today, we're going to crack that code. We're talking about a technique called diagonalization, and trust me, it unlocks some serious mathematical superpowers. So, to get us started, let me just throw this question at you. Say I give you this matrix, we'll call it A, and then I ask you to figure out what A to the power of 100 is. I mean, where would you even start? It sounds like a complete and total nightmare of a calculation, doesn't it? And yeah, you'd be absolutely right. If you just tried to brute force it, you'd have to multiply the matrix by itself, and then multiply by itself again 99 times in total. That's just an insane amount of work. You're bound to make a mistake, and it's just not a practical way to do things. This is exactly the kind of problem that forces us to look for a smarter path, a secret shortcut, and that shortcut is hidden inside the matrix's DNA. Now, the first piece of this secret code is something called an eigenvector. So think about it like this. When a matrix acts on the space around it, most vectors get totally knocked off course. They point in completely new directions. But eigenvectors, they're special. They're kind of like a compass needle. No matter how you warp the map around it, that needle holds its ground, always pointing in its own true north. The only thing the matrix can do to it is make it longer or shorter. And if the eigenvector is the special direction, then this guy, the eigenvalue, is the other half of the code. We use that Greek letter lambda for it. The eigenvalue is the scaling factor. It's simply the number that tells you exactly how much that special eigenvector gets stretched or shrunk. It's basically the strength of the matrix's pull in that one special direction.
So you take those two ideas, eigenvectors and eigenvalues, and you put them together, and you get this beautiful equation right here. This is it. This is the master key. This is our Rosetta Stone for decoding what a matrix is really doing. It tells us that our complicated matrix A can be broken down and rewritten as a product of these three other matrices. This is the absolute heart of diagonalization.
Let's actually break down what each piece is doing here. You've got A, our complex coded message. Then you have P. P is built using those special eigenvector directions, and it acts like our language key. It lets us change our perspective to translate the problem into a much, much simpler world. And D? D is the prize. It's the simple, decoded message. It's a diagonal matrix, which means it only has our special eigenvalues on the diagonal and zeros everywhere else. And its effect is super simple. It just stretches space along its main axes. Okay, so this whole thing seems amazing, right? Like a universal decoder for any matrix. But here's the twist. Can every matrix be decoded this way? Can we always find this secret code? Well, the answer, and this might surprise you, is no. There's a critical make-or-break test that a matrix has to pass before it's allowed to be diagonalized. And this is the test. It all comes down to comparing what I like to call the promise versus the delivery. On one side, you have the algebraic multiplicity. That's the promise. It's how many times an eigenvalue pops up as a solution. So, if an eigenvalue shows up twice, the matrix is promising you two special independent directions. Then on the other side, you have the geometric multiplicity, and that's the delivery. It's the number of actual independent eigenvectors you can find for that eigenvalue. So here is the one rule to rule them all. It's the golden rule. A matrix can be unlocked, it can be diagonalized if and only if, for every single one of its eigenvalues, the promise equals the delivery. The algebraic multiplicity has to perfectly match the geometric multiplicity. If even one eigenvalue fails this test, if the delivery falls short of the promise, the whole thing is off, and our master key just won't work.
Now, the actual process for doing this follows a pretty logical game plan. Step 1, you hunt down the secret numbers, the eigenvalues. Step 2, for each of those numbers, you find its secret direction, the eigenvectors. Step 3, and this is the big one, you run the test. You check, does the promise equal the delivery? And if it passes, you move to step 4. You build your code, assembling your language key, P, and your simple decoded message, D.
All right, we've got the code, we've got the key, and we know the rules. So now, let's unlock the superpowers. Let's circle all the way back to that impossible problem from the beginning, remember? Calculating a matrix to the 100th power. With this new tool in our hands, it becomes, well, you'll see, it becomes almost trivially easy. Check this out. Since A is the same as P times D times P inverse, A to the 100th is just P times D to the 100th times P inverse. And here's the magic. What's D to the 100th? Well, since D is a diagonal matrix, you just take each number on that diagonal and raise it to the 100th power. That's it. That impossible 99-step multiplication nightmare just turned into 2 easy matrix multiplications and a few simple calculations. It's an absolutely incredible shortcut.
And that's just scratching the surface. This one technique lets you compute massive powers, sure, but it also lets you compute things called matrix exponentials, which are absolutely crucial in fields like physics and engineering. It's the key to untangling and solving complex systems of differential equations. It even lets you find a matrix's determinant and trace instantly. You just multiply or add the eigenvalues. The list of superpowers just goes on and on.
Let's just zoom in on one of those superpowers for a second, solving coupled systems. You might start with a total mess, where all your variables are tangled up and affecting each other, but then you use your language key, P, to change your perspective. And in this new eigenvector language, the whole system becomes decoupled. It breaks apart into a bunch of simple, separate equations that are a piece of cake to solve. Then you just translate your simple answer back to the original language. It's elegant.
Now, we said not every matrix can be diagonalized, but there are a couple of really important families of matrices where it's always guaranteed. If you find that a matrix has all unique, distinct eigenvalues, you're golden. It's a guaranteed pass. And even better, there's a powerful result called the spectral theorem that tells us that every real symmetric matrix, that's a matrix that's a perfect mirror image of itself across the main diagonal, is 100% guaranteed to be diagonalizable. No test needed.
So that brings us back to the big question, right? What happens when you do run the test and a matrix fails? What's the backup plan when the promise is bigger than the delivery and you just don't have enough eigenvectors to build your key? Is that just it? A dead end?
No, not at all. There is a plan B, and it's called the Jordan normal form. You can really think of it as the next best thing. It's a method for getting any matrix into a nearly diagonal form, even the ones that are missing eigenvectors. In fact, the Jordan form is the more general tool that always works. And that makes our beautiful, simple diagonalization the most perfect, ideal special case of it.
So, what are the big things to take away from all this? First, diagonalization is all about decoding a matrix into its most basic actions and directions, its eigenvalues and eigenvectors. Second, the test is simple. For every eigenvalue, does the promise equal the delivery? If the matrix passes, it gains some amazing superpowers that make hard problems easy. And if it fails, no sweat, because the Jordan form is always there as a backup plan.
And to wrap this all up, I want to leave you with one final kind of mind-bending thought. It turns out if you have 2 different matrices that can be unlocked by the exact same key, the same P matrix, it means that they commute. It means that A times B is the same as B times A. Now, in the very weird world of quantum physics, that mathematical fact has a huge physical meaning. It means you can measure the properties that those matrices represent at the exact same time. So, what do you think this shared secret language, this common key, really tells us about the fundamental structure of our universe? Something to think about.